Okay, so we're looking at the worksheet called friction problems. This is really kind of taking us through a bunch of step-by-step process. You know, there's an A, there's a B, there's a C, there's a D. But really what we could do is, as we get better at these problems, it's just going to say, like a 10 kilogram block is being pulled at a constant velocity by 20 newtons force to the right. What is the coefficient of friction between the block and the surface? Okay, so that's kind of where we're going to get to. But we're going to kind of do some of the intermediates along the way, and that's why there's all these kind of steps. So we did your homework was to do free body diagrams with friction over the weekend. That free body diagram with friction was a lot like this, but it was just kind of filling out the numbers and then that was the end. This is kind of going through and doing some like questions that would go with it. A free body diagram is always where I think you should start, and you should label all the forces, and I like to fill in all the numbers. Now you can say, do I really need to fill in all the numbers every single time? No, you don't have to. However, as we get into these friction problems, you're going to find out that that's really the reason why I'm going to hope that you realize that the reason why I've been pushing, like, what is your gravitational force? What's your normal force? All along the way is because we're going to need that here. Well, you don't have to. You could just kind of go ahead and say, well, what forces are acting on this thing? Well, it says a 10 kilogram block is being pulled at a constant velocity by a 20 Newton force to the right. It's being pulled, I'm going to call that an applied force. So my applied force is 20 newtons to the right. By name, we could probably say, well, it's sitting on a surface, therefore there's a normal force. It's on Earth, which has a gravitational pull, so there's a gravitational force. That's the only ones I know of at this exact moment. What we will find as we read on a little bit is like, what is the force of friction? That is going to be a force of friction, but we don't necessarily know that with the information given yet. Key thing, constant velocity. What does constant velocity tell me about my acceleration?
Zero.
Acceleration is 0. If my acceleration is 0, what does that tell me about my net force? Is what? Remember, F net equals m times a. So if a is 0, then F net must also be
0.
Okay, and what's true about my forces? Are they balanced or unbalanced?
They're balanced.
In which direction are they balanced? X, Y, or both? Both, yeah, they're both. Now, an object can be moving with a constant velocity in one direction, but it could be accelerating in the other. It's not, it could. We're not dealing with that. So just kind of keep that information in mind. So the fact that my forces are balanced, my picture doesn't show balanced forces. So in order for my forces to be balanced, there must be some force going to the left. And what would the value of that force have to be?
The same as the applied.
Which is, yep, the same as my applied, which in this situation is 20. Now what we're going to find once we read on is that's the force of friction. And what's true about my gravitational force and my normal force? Are they balanced or unbalanced? Is it accelerating in the y direction?
No.
Are the net forces, are my forces balanced or unbalanced in the y direction?
Balanced.
They're balanced. So these are also going to be balanced. Now you could say, well, I don't care, I don't want to fill in those numbers. Okay, we don't have to yet, but we're going to very, very, very quickly. To answer question number 1, or part A, what is the net force? The net force is 0. And the reason why that net force is 0 is because it said my velocity is constant, which means my acceleration is 0, my net force is 0, my forces are balanced. That one statement tells me all 3 of these other statements are also true. There's no calculation for net force. For part B, we really don't need to do a calculation for that one either if you understand what balanced forces it is. What it is saying though is the sum of all my forces in the x direction is equal to F net in the x direction, which is equal to mass times acceleration in the x direction, which both of those are 0, right? F net was 0, acceleration was 0. So sum of all my forces in the x direction says I'm going to add my forces going to the right. I'm going to subtract my forces going to the left. And I set it equal to 0. Or I hit a crack in the table. My applied force is equal to my gravitational force. That's what balanced forces tells me. That's why this is 20 and this is 20. Because Newton's second law says my forces are balanced. You don't necessarily have to do that stuff, I'm just trying to show you that stuff. Now, part C, I'm kind of forcing you to solve for normal force in a problem that maybe I won't directly ask you to find normal force, but what if we kind of skip ahead to part D? Part D is asking what is the coefficient of friction? I'm asking you to solve for mu I'm asking you to solve for mu. The only equation that has mu in it is that equation, which needs a normal force. So as we get better with these problems, I won't ask you to find the normal force, but you're probably going to have to find the normal force because we'll be using an equation like that. So what is the normal force? Well, my forces in the y direction are balanced, right? Because we said the forces are balanced in the x and the y. So because my forces are balanced, my ups minus my downs, the sum of all my forces in the y direction, F net in the y direction is equal to mass times acceleration in the y direction, that's 0, that's 0. Add my ups, subtract my downs, they have to add up to 0. Whatever my normal force is, whatever my gravitational force is going to be what my normal force is. There is a formula for gravitational force. It's m times g. So F of g is 10 times 9.8. F of g is equal to 98 newtons. My F of g is equal to 98 newtons. So based on that, my normal force is also 98 newtons. Sorry, everyone.
Oh.
My ears are starting to hurt from my face mask straps behind my beard. All right, so force of friction is 20. Coefficient of friction, we don't know. Normal force, 98. Divide both sides by 98. Coefficient of friction, or mu, is equal to 0.2. Oop, you couldn't see any of that, my apologies. It's a coefficient, it's a number, there is no unit associated with it, it's simply 0.2. 0.2. That's a coefficient of friction. I'd like you to try number 2, part A and part B. And just kind of, I'd say pause at part B. So, well, I guess you wouldn't have to pause because you can check to see if you have the right answer there listed. Go about, I'm going to say 5 minutes. not for this one. There's a,
Well.
there was a sheet with an equate, that was posted in Canvas. File that. I can try to find it. We filled that in.
Yeah, I had the coronavirus.
I'm guessing we checked that, we filled that in on November 30th would be my guess. And if you look in November 30th, Monday, 30th, it should be filled in. I have a filled in one somewhere here too. I can get you a copy to look at. I think. 2 minutes left. I gotta send an email really quick to Mr. Right there. Sorry, everyone. Sorry about that. 3-minute diagram. 3 kilogram object, kind of like putting that in there as a placeholder. Initial velocity is 10 meters per second. When it hits a friction surface with a coefficient of friction of 0.1. I'm telling you mu is 0.1. That is not the force of friction, that is the coefficient of friction. Coefficient of friction. So, what forces are acting on this thing?
Gravity.
We have gravity,
Normal force.
we have a normal force,
Friction.
we have a friction, and we know there's a force of friction because there is a coefficient of friction. If coefficient of friction is 0, that'd be frictionless, then there'd be no friction. But there is coefficient of friction, therefore there is going to be friction. Anything else? Some people say, well, the object's moving 10 meters per second, therefore there's got to be an applied force, right? Is that bowling ball moving right now? Sorry. Yeah, and was I pushing on it the whole time it was moving?
No.
Did I apply a force at some point?
Yeah.
Yeah, it caused an unbalanced force, therefore it accelerated. But once it was going, I didn't have to keep pushing it, right? Can an object be moving without an applied force? Yeah. Okay, it's possible. That's it for forces acting on this thing. So what is the force of friction? Well, there's 2 ways we can find force of friction. We could sum up my forces in the x direction and set it equal to mass times acceleration, which we don't know yet. Or we could use its own special equation that says force of friction is equal to mu times our normal force. Now, we know mu is 0.1, so we know mu here is 0.1. So we can say f of f is equal to 0.1, and all we have to do is multiply it by our normal force. So we got to fill in some of this stuff. So do you have to fill in all these forces? No, but when we get in forces, you're probably going to have to. So how do we calculate f of g? M times g, and m is mass, which is 3 kilograms. G is our gravitational acceleration, and on Earth, that's 9.8, and 3 times 9.8 is 29.4. So this is 29.4. That's my f of g. That is the weight of this object, because those are, f of g and weight are the same. F of g and weight are the same. What about my normal force? Am I force in the y direction balanced or unbalanced?
Balance.
Right? It's not accelerating into the air or down through the surface, so my forces are balanced. So my ups minus my downs have to add up to 0 in the y direction. My normal force is 29.4. So then we can use that over here, 29.4, to determine that my force of friction is 2.94 newtons. Now, how did I know my force of friction was to the left? Because this is an implied velocity of positive 10, right? It's a positive, it's not negative 10, it's 10. So that's implied as a positive. Velocity is to the right when it's positive, and friction always opposes motion, so therefore friction is going to be to the left. That's why that left is listed here. And we can say that the thing's moving to the left. Now there's 2 ways we can find acceleration for part B. In part B, if we knew enough Fab 5 stuff, we could do a Fab 5 problem. There's 5 variables in Fab 5. Displacement, initial velocity, final velocity, acceleration, and time. We need to know 3 out of those 5. How many Fab 5 things are given in this problem? Only 1 so far, right? What is the acceleration of the block? Now, if you look ahead to part C, you say, wait, it comes to a stop. Okay, now we have 2. So we have initial velocity, we have final velocity. My apologies. The camera hopefully didn't see me. My fingers were maybe inappropriate. My apologies. I was just trying to go 1 and 2, but yeah, sorry. We'll edit that part out maybe of the video. Okay, we have 2 parts. Okay, we have 2 Fab 5, and that's it. We don't have enough Fab 5. Don't worry, Mr. Davies. No one watches those videos anyways. Yeah, maybe someone does. So we don't have enough to do Fab 5. That's my point. So in order to do a Fab 5, then we're going to have to find acceleration. The other way we can find it is we can sum up all of our forces in the x direction, which is equal to F net in the x direction, which is equal to mass times acceleration in the x direction. That's Newton's second law. There's 3 parts to it, and we really only ever use 2. Since I don't know what my net force is, and it's not asking me what my net force is, I'm just going to scribble that out. I'm going to say the sum of my forces is equal to m times a. And what I'm really concerned about, what I'm trying to determine, is that a. The sum of all my forces, if we're talking about my y's, it'd be add my ups, subtract my downs, set equal to m times a. Since we're talking about the x, though, it's add my rights, subtract my lefts, set that equal to m times a. So we add all of the forces going to the right. In this case, there aren't any. We subtract our forces to the left, and we set that equal to mass times acceleration in the x direction. We can fill in numbers. We just determined f of f, so this is going to be minus our 2.94 because we subtract our left, so that's why that's a minus, is equal to the mass, which is 3, times acceleration in the x direction, divide by 3, divide by 3. My acceleration in the x direction is going to be negative, which tells me the direction of 0.98 meters per second squared. My acceleration is going to be to the left because my forces are unbalanced to the left. Okay with that? Questions on that? Yeah.
So, oh wait, never mind, I answered.
What's that?
Never mind.
You sure?
Yeah.
Okay. Anybody else? Okay, part C, now it's saying how long. What am I asking you for? Time, right. Time is not a force problem. Time is a Fab 5 problem. So we could go Fab 5 to acceleration. Once we know acceleration, I don't remember if I talked about this with your class or not. Did I talk about this with your class? Yes, no?
Yeah.
Okay, so we just went this route. We went Newton's second law to acceleration. We're trying to find a time. So the idea is now I can use that acceleration to do a Fab 5 problem. That's where we're at. So because how long is a measurement of time, could be a distance, but that's not how this is worded. It's a Fab 5. Fab 5 problems from here on out are only going to be 1D motion Fab 5 problems, just for the record. So this is a 1D in the x direction. We're talking about the box moving in the x direction. So delta x, vi, x, vf, x, a, x, and t. We knew the initial velocity is 10 meters per second, because it says that right here. Because it says how long does it take to come to a stop, we then can say my final velocity is 0. My acceleration is negative 0.98 meters per second squared. And that came from our Newton's second law. And then we're trying to determine time. So we'd have to pull out our equation sheet on Fab 5 problems Number two, VFX is equal to VIX plus AX times T. Final velocity is 0, so 0 is equal to 10 plus negative 0.98 times T. We have to subtract 10 to the other side, and that's equal to negative 0.98 T. T is equal to 10.2 seconds. Now, part D, we're just gonna talk about. Part D says how far does the block slide? Now I'm asking you to solve for displacement, I'm asking you to solve for delta X. It's another Fab 5 problem. I'm just not gonna take the time to do it at this point. It's the same idea though. We had to use the acceleration from our Fab 5 to go through and determine that. Why don't you try number 3 on the back? 5 kilogram block is being pulled by a 5.5 Newton force at a constant velocity. Find the coefficient of friction. Solve for mu. We'll go 5 minutes.
Here's your sheet.
Okay. Peyton, this string of sentences right here is kind of an important one.
It is important?
Yeah.
I
So,
did.
so like that idea of my velocity is constant gives us a fair amount of information from those statements because of that. All right. So that was 5 minutes. 5 kilogram block is being pulled. Constant velocity. Constant velocity tells me my acceleration is 0 or not 0,
It is 0,
which means my F net is,
also 0,
which means my forces are.
balanced.
Okay, so that's kind of something to keep in mind and as we kind of do this. So we have our 5 kilogram block. We have applied force of, oops, I poorly planned that, 15. Have applied of 15.5 newtons. What other force are acting on this thing?
Gravity.
And that value is 49. That's because M times G is F of G. We take 5 times 9.8. 49 newtons. Okay, what else?
Normal force.
What's true about my normal force and gravitational force?
The same.
They're the same because my force in the y direction are balanced, therefore my normal force is also going to be 49. What else?
Friction.
And the reason why we know there's a force of friction is because it's asking for the coefficient of friction. If the coefficient of friction was 0, then it'd be frictionless, but we're going through and basically saying, hey, there's some force of friction, and I don't know what that is. Actually, we do know what that is. Never mind. Okay, there is a force of friction. What is that force of friction?
15.5.
Because
the forces are balanced.
Because my forces are balanced. Forces are balanced, therefore that's equal. So then, once we have all of this stuff filled in, the question being asked is really just this. Solve for mu. So because my forces are balanced, my force of friction is 15.5. Times is equal to mu times my normal force. Because my forces in the y direction are balanced, my normal force was equal to 49. Divide both sides by 49, divide both sides by 49. Mu is equal to 0.3163 something. It's a coefficient, it's a number. There are no units associated with it. All right, we're not going to do that last one, just for the record. I do want to talk very briefly about some situations. If I had a 10 kilogram object, I'd have an F of G of 98 newtons. Now, if it's just sitting on the surface, what's true about my forces in the y direction?
Balanced.
Therefore, my normal force is going to equal 98 newtons. Good. Same 10 kilogram object, which means F of G is still 98 newtons. If I were to lift upwards, if I were to apply a force of 10 newtons, is that possible?
Sure it is.
Sure it is. What happens to that object?
There's less friction.
Nothing to do with friction on this one, actually. What happens to that object? What's that?
Goes up.
So let's pretend these are pounds for a second. If I have a 98-pound object sitting there and I pick up with 10 pounds worth of force, what happens to that object?
Wouldn't move.
It doesn't move, right? But according to that picture, my forces are balanced or unbalanced?
They're unbalanced.
According to that picture, they're unbalanced, which would mean it's going to accelerate which way? Down, through the surface, right? Through the floor. That's not going to happen. But it is in contact with the surface, so therefore, what force is acting on this? There's still a normal force. What's the value of that normal force now? Is it still 98? It's 88, right? my forces are balanced in the y, oops, 88. 80, sorry, I have whiteout, I should just use it. Equals 88 newtons. My forces are balanced. My ups, 10 plus 88, minus my downs, have to equal 0. It is possible, right? Think about, like, if you're standing on a scale, or your friend's standing on a scale, and you come up and grab them by the elbows and you pick up words on them. You're gonna lift them off the scale, but what happens to their weight according to the scale? It goes down. That's what your normal force really kind of is. That's what I think of it, is what the bathroom scale would read. Same thing, I used to always kind of like to do this. I thought it was funny. Other people didn't think it. But you'd get certain athletes, I won't name them by what event they participate in, but seem mighty concerned about their weight. And I always thought it'd be fun to kind of step on their scale, just kind of push on a little bit, because they're like, because we didn't have digital scales back then. It was a long time ago. And they'd be like, oh my goodness. Because they were worried about like a couple pounds, and all of a sudden their scale read like 10 pounds, and then they saw me, and they'd be like, oh, that was silly, that was funny.
That's so silly.
Yeah.
That's what they told me. They didn't hit me or anything.
Then I'd get angry at them when people did that to me.
No, they wouldn't. But see, times were different. Back in the good old days, we didn't hit each other over things like that. We just used our words and expressed our feelings.
Oh yeah, totally.
That's how we used to do it back in the good old days. So the idea is your normal force number could change. This problem I'm not going to do with you, but basically that's what this was saying is if I had an applied force of 10, if my velocity was constant, that means my force of friction had to be 10. So what would I have to pick up with in order for this to be 10? Because what you're really messing with is by applying this upward force, you're changing the normal force, and then by changing your normal force, you're changing your force of friction. It was a way that we could kind of force some of those things, and I'm not going to take the time to do that. But that's what that problem is. The point I want to make is it is possible to have something, a normal force that doesn't equal your gravitational force. We've kind of gotten in that habit, I think. But with a few minutes that remain, I do want to wrap up this pulley lab. On last week, Monday or Tuesday, and we finished it on Wednesday or Thursday, we did a pulley lab. Now this is the pulley lab, the virtual part, that if you weren't here from a computer, you should, fingers crossed, be able to allow Flash to work, and you should be able to do this. If not, I still have some stuff set up. Actually I have 1, 2, 3 out of the 5 pulley configurations actually set up right now. But the idea is, from a pulley configuration, we can change and we can vary things, and I'm just gonna make this 10 to make it. So what we called F of G, they call load. So the load on our pulley configuration is 10 newtons. And in this pulley configuration, if I want to lift this thing, I need to apply 10 newtons worth of force in order to pick this object up. The ideal mechanical advantage, something that I gave you and I asked you to calculate the observed mechanical advantage, is 1. It's a ratio between the load and the applied force. It's also a ratio between the distance moved and the string pulled. You measured both of those things. You measured how high did the object lift, how much string did you pull, you looked at that ratio, and you looked at the applied force versus the force of gravity. On the concept portion of a test, I'm going to ask you to say, hey, what's the mechanical advantage of a pulley configuration? And visually, you can determine this by looking at the object and how many strings is this thing being held up by?
1.
Yeah, right here, right? This string has all of the weight on it. So that's 1. It's a 1-to-1 ratio between applied force and load and string pulled versus height lifted. If we change it to, this one is kind of, I don't think I've ever used a pulley configuration like this in real life. But if your pulley was below you, you could pick up on the object and pull it up. It's called a single movable pulley. So let's say you had a tree house and you had something that was like 10 pounds. We just want to pretend these are pounds. In order for you to lift that, you'd only have to apply 5 pounds worth of force. It's half, right? It's mechanical advantage is 2, it's half the force. And how many strings are sharing the weight of this thing? 1, 2. There's 2 strings that are sharing the weight of that object. Mechanical advantage is 2. The trade-off is, in order for me to lift it 0.2 meters, I had to pull 0.4 meters worth of string, twice as much string for half the force. We could go, this is called a single compound. We call it, the lab called it a single fixed, single movable. Same idea, how many strings are holding up that object? There's only 2, 1, 2. Okay, this string is not sharing the load or sharing the weight. However, the one that we pull on here is, that's the slight difference there. This is again mechanical advantage of 2, therefore half the force. Trade-off is 2 times the string. If I uncheck this box and I go to this one and I change these, that to that, I zoom really far in. If we were to say how many strings are holding this thing down here, 1, 2, 3, 4, 5, 6. Based on that, we should have a mechanical advantage of 6, which then means we pull 1/6 the force, but as a response, or as a result, I should say, we have to pull 6 times the amount of string. So there's a trade-off with pulley, or I shouldn't say pulleys, with simple machines. The more force you apply, the less string, the less force, the more string. So why would you use a pulley configuration like this? It's a really heavy object that you're trying to pick up. There's a trade-off. The trade-off is more string. I don't even know if we'll see our number once it printed it up. Hey, there we go, 1.2 meters, so it's 6 times the amount of string. Okay, from a picture, if you count how many strings are sharing the weight of that, that's how you can determine. Watch out, there's a bowling ball here. It's kind of hard to see a bowling ball when your beard is so long. You can determine your mechanical advantage of it. Questions about pulleys? Mechanical advantage, like I said, I'm going to ask you probably to identify the mechanical advantage of a pulley configuration. Okay, on that coloring pencil box is a worksheet. It's called Example Friction Problems. There are 5 problems. I unfortunately don't have the answers. I want to show you really quick before I know we're getting close here. They don't have any answers, so I apologize for that. When I post this in Canvas, because I also apologize for not having this posted in Canvas yet, I will post the answers, and I'm just going to arbitrarily call this problem number 1, 2, and 3. Problem number 4 and 5 are on the back, but they do have an answer. Okay. Number 1, find the acceleration given this free body diagram and a coefficient of friction of 0.5. Find the applied force if the constant velocity is this, and this is the information you have to work with. That's the idea. When you get to the back, now you're going to do some Fab 5 stuff. A 6 kilogram block is released at 15 meters per second with a coefficient of kinetic friction. Ignore the kinetic friction part. We don't care about that yet. Coefficient of friction is 0.5. How far? That's a Fab 5 in order to come to a stop. So there's 5 problems. If you have questions, let me know on those. But that's your friction problems. Don't forget about the group of reindeer.
Oh, I get it, 'cause it's almost Christmas.
Okay. So, if you have questions on that, please let me know. Have a great day. We'll see you next time.